We look up and see cotton balls slowly drifting across a blue sky. It's a peaceful, almost entirely passive image. But that serene perception hides what is actually sitting above us: massive, highly active physical engines. Right now, these atmospheric structures are blanketing roughly 70% of the Earth's surface. And when one of these engines stalls over a populated area, the volume of water it holds becomes an immediate threat. A sudden, localized downpour can dump hundreds of millimeters of rain in a matter of hours, triggering flash floods that swallow highways and paralyze infrastructure. Scale that process up, and you get continent-threatening storm systems. As water vapor condenses inside that swirling mass, it releases heat. The total thermal energy generated by this single physical process in a mature typhoon equals 10,000 times the energy of an atomic bomb. So how exactly do invisible, microscopic water molecules floating in the air manage to combine and generate a physical force capable of tearing apart modern civilization? It starts at a microscopic level, with a process known as cloud microphysics. Invisible water vapor suspended in the atmosphere relies on microscopic dust or salt particles to provide a surface for condensation. Once they latch onto these specks, the molecules rapidly swell into tiny spherical droplets, usually measuring just around 2 micrometers wide. When vapor turns into liquid, it undergoes a phase change that releases a specific type of thermal energy, called latent heat, directly into the surrounding air. Multiply that tiny release of heat by billions of droplets, and the air inside the newly forming cloud quickly grows warm. This diagram illustrates what happens next. Warm, buoyant air creates aggressive, rising convection currents that pull moisture up from below. These continuous updrafts act like an atmospheric elevator, forcing the cloud structure to punch tens of kilometers into the upper atmosphere. Humanity has systematically tracked these chaotic growths for centuries. What we've found is that depending on their altitude and the surrounding temperature, these moisture engines consistently form into one of 10 fundamental architectures. These are highly organized physical structures governed by strict thermodynamic laws that allow us to observe, measure, and calculate their evolution with mathematical precision. This chart highlights how these structures operate as the Earth's primary thermostat. During the day, their tops reflect short-wave solar radiation back into space, cooling the planet. Simultaneously, they act as a thermal blanket, trapping long-wave radiation from the surface and keeping heat in. Even minor fluctuations in this specific physical feedback loop can alter the amount of heat our entire atmosphere retains. Shift that delicate balance just a fraction, and it triggers extreme weather anomalies and disrupts global precipitation paths. To keep up with these massive shifts, modern meteorologists rely on advanced observational tools. We use specialized radar systems to penetrate these dense, swirling systems, tracking their liquid water content and wind speeds in real time to predict their next moves. In a warming climate, the interaction between vapor and heat determines where rainbelts shift and how much thermal energy stays trapped near the surface. Unlocking these mechanics provides the data needed to predict the future stability of the global food supply and the safety of coastal populations. Welcome to the study of cloud physics.